it is very rare for you to have an isolated charge. In general, you have many charges that are sitting around all together. So how do you account for that? So there are 4 things that we are going to talk about. Continuous charge distributions. Okay, so I'm going to cheat a little. So I'm going to include point particles when I'm talking about charge distributions. So they're not quite continuous, but let's see how it goes. So for discrete point charges, can I write my E field as the sum over Qi divided by Ri squared Ri hat with a K outside, where I is the sum over 1 to n. Provided I have n is the number of charges present. Everybody understands how I got that, right? It's just I'm taking the sum. Now, how do I go from these discrete point charges to having many charges together? If the sum becomes very small, what do? Instead of writing sum, we'd write integration. So for continuous charge distributions, I could have charges distributed over some region. I could have charges spread along a line. I could have charges spread over a surface. And number 4, I could have charges spread over a volume. Okay, so if I have charges spread over some region, I don't know, a region, can I take this region to be made up of tiny elements? May I call those tiny elements dq? So then how will this equation, let me call this equation A, change? My sum became my integration over the small dq's that I have now. When I have the charges spread along a line, can I do the same thing? But in this case, I will have something called the linear charge density. lambda. And lambda is charge per unit length. So may I write this as small dr's as I go up forward? E equals K lambda R hat divided by R squared DL. I'm gonna move this down a little, give myself more room. When I have charges spread over a surface, instead of a linear charge density, I will get, what is it called? Oh, surface. Surface charge density. And that is sigma, which is charge per unit area. In this case, E becomes K sigma integration Oh, everybody understands how I'm replacing them, right? Because this implies that my dq will now become sigma dA. So I am replacing my dq's everywhere. And this implies dq will become lambda delta L. And when I have charges spread over volume, I will get volume charge density, rho, which is nothing other than charge per unit area. Oh, no, sorry, charge per unit volume. Or in this case, my dq will become rho dV, and my E will actually be K integration lambda R over R squared dV. What was R again, guys? R was called the separation vector. The separation vector tells you your source from your field. I want you to be very careful. I want you to write on a sticky note. I want you to make this picture. I want you to make a Q here, and I want you to make a dot here. Actually, let's call this point P. Griffith calls this your separation vector, that funny looking R. Where he says that this Q can be replaced with whatever you have. Surface, volume, a collection, whatever that Q may be, that's there. And P is the point where you want to find your E field or your B field or whatever field you're looking for. P is that point that you want to find. So this is going to be your field, and this is what he calls the source. And if you were to replace this with Coulomb's law, what would you replace that P with? Q2. So Q is the thing that's causing the electric field. P is what you are going to, where you're going to place your test charge to check how much E is being produced by the thing that you're looking at. Okay, now this thing that we drew here, the lines are called what? Field lines. These lines are called field lines. These field lines, they are becoming smaller and smaller as they go far away. Now you may be wondering why we keep putting these R hats into here in every single one of these formulas. Why don't I just take them out of integration? Why do I have to have them in the integration? The reason why I have to have them in the integration is because R hat is not constant. It changes as you move. Do you see that? So in fact, it becomes part of the integration and you cannot just ignore it. Does that make sense? So it will become a part of your integration, and you will have to worry about this R hat when you do these integrations. Okay, so what is the most simplest possible case? The simplest possible case is this one. What does this represent? The field created by a point charge Q. That is the absolute simplest case. Any of these other ones become complicated.